Hello students, welcome to our channel's Maths Academy. Now today we are going to discuss third lecture of Ioqm number theory. Today our topic is, in this lecture we mainly discuss division algorithm. So here main purpose of this lecture is division algorithm. The class where the first division starts. Knowingly or unknowingly, a student know about this technique or the divisions. So in division algorithm, statement is like that: given any integers a and b, given any integer a and b with a not equal to 0, divisor is not equal to 0, there exist unique integers. There exist unique integers q and r such that b is equal to b is equal to qa plus r. So there exist two unique integers q and r such that b is equal to a times of q plus r, aq plus r, where 0 lesser than equal to r lesser than mod of a. 0 less than equal to r less than equal to mod of a. If a does not divides b, then the stronger inequality is, then if a does not divide b, then satisfies, then r satisfies the stronger inequality. The stronger inequality. Zero lesser than r lesser than mod of a. Consider some example. Let b is equal to 1 minus 2 61 minus 59 and our a is equal to, divisor is equal to, suppose minus 7. So 1, when you are going to divide by minus 7, I take the quotient is 0 and the remainder is 1. Here this is a, this is b, here you are getting q and here is r. This is known as divisor. B is called dividend. Q is the quotient. R is the remainder. So always remember, remainder is non-negative. That means remainder either 0 or positive. So here this is our remainder. This is the number a, and here I am getting q, and this will be the value of b. So if I have minus 2 and I am going to divide by minus 7, so what will be the remainder? Remainder should be greater than equal to 0 and less than mod of 7. So if I put here if I put here 1, so it will be minus 7. Okay, but we want minus 2, so here should be 5. So it follows the inequality because our remainder lesser than the divisor and greater equal to 0. So our remainder is 5 here, which is greater equal to 0 and less than the divisor, like this. So it cannot be numerically greater than 7. So if I have 61 and you are going to divide by minus 7, you want some remainder. If exists, it is positive. So you should simply do the division by 8. 56 plus 5, 61. If you have 59 with negative sign, then dividing by minus 7, so if you take 9 times, so here you are getting 4. Okay, so these are the examples of the division algorithm. Now we are going to talk about the application of this theorem. So now deal with the question number 1. Show that the expression a multiply a square plus 2 divided by 3 is an integer for all n greater than equal to 1. Okay, now so this we have to prove this will be an integer. If you look at the denominator is 3. Okay, now so we have to prove this whole thing is divisible by 3, then you are getting the integer as the quotient. Okay, now so now show that this is integer for all n. For all, here n is not given. For all a, I think it will be for all a greater than equal to 1. A is what? A is the integer. So now suppose any integer, think about that, any integer a, when we are going to divide by 3, then the remainder will be either 0 or 1 or 2. That means this number a I can write as some quotient plus remainder, or it will be in the form 3q plus 1, or it will be 3q plus remainder is 2. So now any integer a can be taken as 3q plus 1, 3q plus 2. Any integer is of the form this one, any one. So case 1, if a is equal to 3q, if a is equal to 3q, then in the place of a put 3q, so you are getting simply it is an integer. So this one is integer. Case 2, if a is equal to 3q plus 1, then in the place of a put 3q plus 1. here you have 3q plus 1 whole square, 9q square, 6q plus 1 plus 2 dividing by 3. So first one as it is 3q plus 1. From the last term you can take 3 common, so it will be 3 2s are 3 3s are 9, 3 2s are 3 1s are, divided by whole 3. 3 and 3 cancel out. So you notice that it is also an integer. Similarly, case 3 you can try at home. If a is equal to 3q plus 2, then again you are getting this expression will be an integer. So now this completes our proof, hence proved. For all a, it is an integer. So case 2 is the homework. Try to solve at home. Going to next question. This is important. Question number 2. Prove that no integer in the following sequences is a perfect square. So the sequence is 1 1 triple 1 4 1, in this way it is going on. So no term of this sequence is a perfect square. Okay, so now how to solve this question? Consider any integer a. A is an integer. So there are two possibilities are there. It will be either even or it will be odd. Any integer. If it is even, so a we can write as in the form of 2q. If it is odd, we can write as 2q plus 1 for some integers q. Now square of this even integer, it will be 4q square. Even of this odd integer, it will be 2q plus 1 whole square, 4q square, 4q plus 1. If I take 4 common, it will be q square plus q plus 1. That means it can written as pq naught for plus 1. Here I can write as 4q1. So what I notice that if you have the square of any integer which is a perfect square, so if you have a perfect square number and you divide that number by 4, so what will happen? Either that number is divisible by 4 or leaves the remainder 1. So keep this result in mind. Square of any integer on division by 4, it will give 0 or 1 as the remainder. That means if the number is a perfect square, if a number is the integer is the perfect square integer, then if you divide by 4, the remainder will be 0 or 1. 0 1. No other remainder you will get. Okay now. So these results we are going to use. So any integers, suppose a square of a is of the form either 4k or it will be 4k plus 1. for some integer k. Okay, so this result is very important. Now take our first term of the sequence t1, which is 11. So this number I can write as 8 plus 3. This part is divisible by 4 and gives a remainder 3 as the remainder when dividing by 4. So that means we can say that since the remainder is not 0 or 1, so we can say that this is not a perfect square, not a perfect square, because here I use the algorithm for division by 4 only. T2 I have 111. This number I can write as 108 plus 3. So on the division by 4 we get the remainder 3, so it is not a perfect square. If I have T3, which is 1 2 3 4, so it will be 1008 plus 3. So again not a perfect square. So therefore if I have a number here, suppose some number is here tr, which is equal to 1 2 3 4 5 6, in this way going on. How many 1 are there? R plus 1 are present, which I can write as 1 0 0 0 1 plus 3. So how many 0 here present? How many 0 here present? So you notice that if it is 3 1, number of 0 is only 1. If it is 4 1 present, number of 0 less than 2. So here number of 0, how many 1 present here? R plus 1 1 present, so number will be less than 2. R plus 1 minus 2, that means R minus 1 zeros present, zeros present. The last number will be 8, not 1. So what we notice that this part is divisible by 4, divisible by 4 and leaves the remainder 3. So this number we can write as in the form of 4k plus 3. Since on division by 4 we are not getting 0 or 1, we say that the TR is not perfect square. So therefore TR is not a perfect square, is not a perfect square, hence proved. Okay, now for all R, for all R. I hope all of you understand this concept. This is question number 2. Now coming to question number 3. So that square of any integer, so that square of any integer is of the form 4k or 8k plus 1. Any integer which is a square, perfect square, you can write in this form. Let any integer a, so this will be either even or odd. If it is even, we can write in the form 2q. If it is odd, then we can write in the form of 2q plus 1. So case 1, when a is equal to 2q, we can write a square is equal to 4q square, that is 4k, for some integer k. When a is equal to 2q plus 1, then we can write as a square 2q plus 1 whole square, which is 4k square plus 4q square, 4q square Don't take 4 outside, simply first write, then go for the simplification. So it will be what? 4q square plus 4q plus 1. So from here I am taking 4q common, it will be q plus 1 plus 1. Q and q plus 1, these are the product of two consecutive integer. If it is product of two consecutive integers, so it is divisible by 2. So this will imply q into q plus 1 is divisible by 2. So therefore q into q plus 1 we can write as 2 times of q naught. So now what will happen? A square, which is 2q plus 1 whole square, which is 4 times of q into q plus, that is 2q naught plus 1, will be 8 times of q naught plus 1. If I replace q naught by k, so I have 8k plus 1. So what we observe that if you have a perfect square number, so this number will be formed in the form of either 4q or 8q plus 1. 4q or 8q plus 1, or 4k or 8k plus 1. Okay na? Hence proved. Question number 4 is also important. Find all integers n such that n square plus 1 is divisible by n plus 1, is divisible by n plus 1. So now we have to find how many n's are there so that n plus 1 divides n square plus 1. So now n plus 1 divides n square plus 1. How many n's are there? Okay, all of you know these results. N square minus 1, it can be written as n plus 1 into n minus 1. So two factors are there. One is the n plus 1, other is the n minus 1. So we can say that this expression is divisible by always n plus 1, because n plus 1 is a factor. So again, n plus 1 divides this expression also. This expression also divisible by this one. These I called 1, these I called 2. Now here I am going to apply one result. A result is if A divides B and A divides C, then A divides linear combinations of B and C, Bx plus Cy, for some integers x and y. Okay, for some integers x and y. So here I cleverly choose, this is suppose my B, this part is C. So I am choosing here B is equal to 1, not B1, x is 1 and y is minus 1. So here I am choosing x is 1 and y is minus 1. This is our C and this is our B. So now using this result I can say that n plus 1 divides 1 times of n square plus 1 minus plus of minus 1 times n square minus 1. This will imply n plus 1 divides 2, because n square cancel out. So if n plus 1 divides 2, then what are the factors of 2? 2 and 1. So therefore we can say that n plus 1 either will be plus 1 or minus 1, plus 2 or minus 2. So we can write n plus 1 when it is plus 1, n is 0. N plus 1 when it is minus 1, n is equal to minus 2. N plus 1 is equal to 2, then n is equal to 1. N plus 2 equal to minus 2, then n is equal to minus 4. Let me check. Here is not 2, here it will be 1. So n plus 1 minus 2, then n is equal to minus 3. So we can say that n is equal to minus 3, minus 2, 1 and 0. Sorry, 0 and 1. Write in the ascending order. So we first write 0, then 1. So these are the possible values of n for which the given expression is divisible. Hope all of you understand up to this level division algorithms. Then next is we have in the next video where we discuss some important result on divisibility and we will solve few questions. Results like an plus bn, an minus bn, when it is divisible by a plus b or a minus b. On the basis of these results, we will do some important question which generally came in the exam. So till then, bye. Have a nice day. Be connected with us. Thank you for watching my channel.